explained. Have a look. If you don't understand something, let me know. Also, we're not going to do the entire book because otherwise I need 20 hours more, and you will not have the patience to follow me for 20 hours more. Guys, something which is very important, sorry, parenthesis. In this book by Logan, it's plenty of exercises, okay? Try to do the exercises in the chapter that we are commenting in the classes. Because basically the exercises that are going to be in the exam are reformulation of those exercises. I cannot really do anything which is extremely difficult. So try to do those exercises, please, because in this way, if you have some problem in doing the exercise, so the idea of the exam is something like the problems that we are solving here during our lectures. Those that are the exercises that are on the book of Logan are other problems like those ones that you are solving here during the lectures. If you are able to solve those exercises, you are able to pass the exam, basically. Please pass the exam, because I do not want to repeat exams. Okay. Then I had some comment also about the exam, because there was a colleague of yours, Michael, what's the name? Michael. It's Michael. Who was asking if it was possible or not to do the exam in the format that I proposed with this review, with this tesina, with this thing. So I was suggesting if it was possible or not to do this as a group work. So I didn't, frankly speaking, I didn't think about that. In any case, I can also agree, but no more than 2 per group. Consider the fact that if you are doing this thing in group, I will be more severe because, of course, I can understand. Ciao, and we've just started. So I can understand if you are alone and you're doing the tesina alone and you are committing some mistake, I can pass on top of the mistake. If you are 2 of you, I cannot be so easygoing. I must be more severe. Third, the oral part, the examination, is going to be individual. So for me, it's fine if you're doing this thing of the tesina together with somebody else, but under these conditions. Okay. Also remember that the topic of the tesina, for those of you that are foreigners, the tesina means basically the project that I was suggesting as a possible examination. So, what about that? I forgot what I wanted to say. The tesina, what about the tesina? The topic of the tesina. Yes, the topic of the tesina must be chosen with me. So, let's try not to do. I mean, the idea is that if we are choosing together, which basically means I'm choosing, because I'm going to suggest some topic. We can agree. Come on, we can agree. You can suggest something, but we can agree on the topic. But in this way, my idea is to have different topics for different people / groups. There is somebody which is asking something on this thing? No, right. So in principle, I should share the screen. Okay. I suppose it depends. I'm sharing. Any more doubts on any other doubts on regarding this thing of the Tesina? For the moment, no. Say it again. Yeah, the record. Yeah, that's fine. Yeah, what about it? No, there is an oral. That's the point. Yeah, with the record, the idea is that you do the presentation, but the presentation, I mean, if you're doing the presentation, I'm asking questions on the presentation. That's the idea of a seminar. Have you ever seen a seminar? A technical seminar? Conference seminar? No. You are doing a presentation, usually 10 minutes, 15 minutes presentation with slides, like the thesis. And then people are asking questions about the topic that you're. But these questions can be something general. So imagine that you are showing me some. Let me give you an example. You're doing some example, you're reporting about some phenomenon, and you are studying the stability of the equilibria or some phenomenon. Then we can discuss about the stability. How does it work? The stability, the equilibrium, the phenomenon. Random question. Random. That's not so random. Actually, it's a question which is related to the topic that you are presenting. That's not a random question. I'm not asking. If you are speaking about the equilibrium, I'm not going and ask you about Markov chains, okay? However, if you're speaking about Markov chain, I can ask you questions about Markov chains, about discrete models. That's the idea. Okay, now come on, let's start the class on the day. We are speaking about Wkb method today. Wkb approximation. Have you ever heard about this? The Wkb approximation? No. All right. What is my paper? Come on, push it. So Wkb approximation. So Wkb stands for Wenzel with N? Yes. Wenzel, Kramers, Bruyuen. Kramers with one N. Kramers, Bruyuen approximation. What's the idea? That's actually a Wenzel, Kramers, Bruyuen. It's a name, you can call it Wkb, doesn't matter. That's actually one of the most important methods of approximation in quantum mechanics. And it's in general a nice approximation method for finding the solutions of ODEs whose highest order in derivatives appears with some epsilon in front. So basically, this is a method that you apply typically to ODEs which are of this form here. Epsilon y prime prime plus q x y equal to 0, where epsilon is a parameter which is well, positive parameter, but very small parameter. It's not applied just to this kind of equations, it's also applied to equations like these ones actually. Y prime prime plus q squared epsilon x y equal to 0, where again epsilon is positive and small parameter, and can also be applied to problems like this one, y prime prime plus lambda squared p of x minus q of x times y equal to 0. In this case, lambda, it's a very large parameter.
Square q
is q squared. Yeah, this is actually like positive definite. So what's new in these ODEs? The first one is the typical ODE to which you are applying the Wkb method. So the highest order in the derivative is appearing with the epsilon in front. In fact, you have these terms epsilon y prime prime. Another thing which is new is that we are considering here equations which have non-constant coefficients. So you have functions here appearing in front of the state parameter y, right? Here there is a q of x. In the second example, I have here another function which is appearing in front of y. In this case, with a variable which is a small variable, because the independent variable, I mean, which is scaled by epsilon. You have an epsilon times x. The third one, it's a kind of special case, because in the third one, if you see, we are considering the case in which lambda, the parameter lambda, is very large. But well, you can do a simple trick. You can just define lambda to be equal to 1 over epsilon, and basically you are turning the equation into an equation where there is the small parameter epsilon appearing. Basically, you are turning the equations exactly into the equation of the first kind, because you can multiply times epsilon squared, and you will have something like epsilon squared y prime prime plus wherever it is later. So yeah, that's the idea. We want to solve. We want to consider one how to find approximate solutions to these kind of problems. At the end of the day, what I will do is just to solve the problems of the first kind, so the first equations. And let's see some case study. Let's see this famous quantum mechanics. Do you have any? Did you have any introduction to quantum mechanics in during your studies? Quantum mechanics, no, in physics?
Nope.
Ah, nothing. All right, all right. We are not studying quantum mechanics. I was just wondering if I can introduce an equation without speaking about these equations, but better not. So the idea is that consider classical mechanics. In classical mechanics, imagine that you have some point mass. So you have a body which has some mass m. This body with mass m is moving along the axis x, and the body is subjected to some conservative force, which means that basically this force can be recovered by the potential under which the body is moving. So the law of dynamics of this body would be something like, well, it's the second law of Newton, and the squared, the squared x in the t squared equal to some force f of x, where the f of x, we say that it's a conservative force. This is minus v prime x, where v is the potential under which the body is moving. If I have this kind of problem, I can add the initial conditions. So I can say that at a certain point, at a certain time t naught, the position of the body is x naught. and at a certain time t naught, the velocity of the body is some velocity v naught. If I have these conditions, if I want to find a solution to this problem, I will find exactly the same solution anytime that I'm trying to solve the problem. We say that this kind of problem is deterministic. So once that you have the equations which is describing the dynamics of the model, once that you assign the initial values, so position at the initial time and velocity at the initial time, then the solution to this problem will always be the same. Always. You can solve the problem 1 trillion of times. Of course, the solution is always going to be the same. That's why actually it's deterministic. Once you have all these things, you can determine univocally what's the outcome of your system with these conditions. In quantum mechanics, things do not work in this way. Quantum mechanics has kind of a probabilistic interpretation. First of all, in quantum mechanics, you cannot define at the same time position and the velocity of a particle, because there is something which is called, and probably this, you have heard about this probably in documentaries, quark, which is called the Isobaric's uncertainty principle, which says that basically you cannot identify the position and the momentum of a particle with infinite precision at the same time. And also another extremely important point is the fact that, yeah, exactly, the point is that you can define these kind of quantities only from the perspective, from the probabilistic perspective. So what you can do is to define the state of a particle in terms of what is called a wave function, which is a function psi of position and of time. Let's suppose that we are just in one dimension, so it's a function of x and t. And what I can do is to define, for example, the probability p that my particles is between has a position which is between A and B. This thing here is given by, I'm going to write this equation. It's something that you don't really need, but just to have an idea. So this probability is given by the integral between A and B of the modulo squared of C. Eh? No. So this thing here, again, gives you the probability for the particle to be between the point A and the point B on the x-axis. If I'm asking, what's this? Why?
Because it's the total probability.
The probability of what?
Of the particle being from minus infinite to plus infinite.
Very good. Yes, that's correct. Actually, this thing is equal to 1 because, well, I'm sure that the particle is somewhere between minus infinity and plus infinity. So that's actually the the only constraint that I have actually on the modulo squared of the wave function of the particle. That's fine. Very good. Fascinating. How do you find then the wave function? The problem in quantum mechanics is that you have to find this wave function, because otherwise I cannot do anything. I cannot do any calculation. Since this is not the course of quantum mechanics, I have to write directly the kind of equation that gives you the wave function of a particle. This is what's called the Schrödinger equation, which tells you I h bar derivative with respect to time of psi, x, and t equal to minus h bar squared over 2m. Well, this is in just in 1 plus 1 dimension, so you have just one space dimension. So derivative, the second derivative of psi with respect to x squared is an x plus some potential Vx times the wave function psi. This is a bit of mambo jumbo. Again, I do not want to derive this. What I want to say is that, well, there are some arguments, physical arguments, that allows you to say that the wave function of a quantum particle must satisfy this equation, this Schrödinger equation. What is interesting is that now what I can do is to assume that the function, the wave function psi, is factorizable. So I can write psi of x and t, of course, as a function of x times a function of t. How did I go here? Phi and what? And y. All right. So I'm writing this as y of x times phi of t. If I'm doing this, let's see what happens to my equation. So taking these ansatz of a factorized function, wave function, I'm putting these ansatz in the Schrödinger equation, and I get I h bar y of x does not depend on t, so this is y of x times the derivative with respect to t of phi. And then on the right hand side I have minus h bar squared over 2m times, again in this case it's phi that does not depend on x. So I can put this phi outside and I have phi times the second derivative with respect to x squared of y plus v of x times psi, which in this case is y of x times phi of t. What can I do now? I can divide by y times phi. So let me divide y times phi, y times phi. Salve. Scusi. E niente. Ciao. Y times phi. Okay. So what I can do then is to simplify y and y, phi and phi, and here I can simplify everything, y, phi and phi. Such a way that my equation, such a way that my equation becomes I h bar dt phi over phi equal to minus h bar squared over 2m 1 over y. Let me call this second derivative of y with respect to x squared. I will write this as y prime prime, okay, plus v. Now, what can we do? Come on, guys. Suggest me some way to solve this equation. What's special in the left-hand side versus the right-hand side? Luca, don't say no. Any idea? Look at the functions, well, at the function that is at the left-hand side, and look then to what happens in the right-hand side. So on the left-hand side, what do I have? I have a derivative of phi, then I have phi. All of these are functions of, just functions of time, right? Because phi is function of time, the derivative of phi is just function of time. IH bar are constant. So this object here is function of time. Function of time. This object on the right hand side is a function of position, of x. Because y is a function of x, y prime prime is a function of x, v, the potential, is a function of x. So this thing on the right hand side is function of position. Okay? There is only one way for having the left hand side equal to the right hand side. And this way, oh no, another beast. Come on, eh?
Is that dimensionless variables?
No. Almost. No, almost. What happens if both are equal to 1? And if both are equal to 1 billion? No, it's 1 billion. If they are both 1035. Is it possible or not? Could be possible. So basically, the only possibility that you have for getting these two things, just to condense these observations, is that these are equal to some constant. So whenever you have these kind of equations where you have the left-hand side, which is a function of a variable, like in this case, time, and the right-hand side, which is a function of another variable, which is in this case position, can be equals, okay? The only possibility that you have to get the left-hand side equal to the right-hand side is that they are separately equal to some constant. Which by chance I call it capital E because this constant is going to be the energy of the particle. So basically this tells me that, well, allows me to split this equation. No, ma perché? To split this equation into two equations, which are going to be now ordinary differential equations. Because now I can write I h bar dt phi over phi equal to E. And the second equation is minus h bar squared over 2m 1 over y prime prime plus v equal to E.
It's not far from the equation of Bernoulli.
It's not far from the
Equation of Bernoulli.
Which one?
This last one.
The second one. All of them are very similar. Now, how can I rewrite the first one? Let me rewrite. The first one as I h bar. This is actually now a total derivative with respect to time because phi depends only on t. equal to E times phi. Correct? Yeah, I can tell you, it's correct. What's the solution of this equation? Come on, this is now an equation that you should be able to solve. Guys, somebody that tells me the solution of this equation. Guys, we have seen always the same kind of solution. Come on. There are just two answers that you can give. One is wrong, but I wouldn't care if you give me the wrong answer. And the other one is the right one. Come on, what are the answers? What kind of solutions have you seen of ordinary differential equations up to now? The typical ones? Ah, very good. That's the right answer. What's the wrong answer? Well, no, it's sine and cosine. But in any case, the right answer is exponential. So actually, the typical solutions that you find for these things, apart for the typical solution that we have seen so far, not the typical solution that you find for these equations. The typical solutions that we have seen so far are either exponentials or trigonometric functions. Well, in any case, this is some constant, let me call kappa, times the exponential of minus e times e over h bar times t. If you don't believe me, take this this solution, put it in the first equation, and try to see if it satisfies or not the equation. I can tell you, it satisfies the equation. Okay, but this is the easy part. What we really would like to study instead is the second one. Now, there is something that I didn't tell you. Well, let me just rewrite this equation in this way: minus h bar squared over 2n times y prime prime plus v of x minus the energy E times y equal to 0. I'm just writing the equation, right? I'm just multiplying times y. There is one important point that I didn't tell you, which is the following. H bar is of the order, does anybody knows the order of H bar? This is the Planck, the reduced Planck constant. No, it's the order 10 to the minus 34 kilograms. 100 units. Well, order of magnitude 10 to the minus 34 in standard system. 10 to the minus 34, it's very, very small. So the idea is that if I'm writing this thing here as epsilon, and if I define this thing here as some function q of x, this is exactly the kind of equations we were saying at the beginning. that should be those to which Wkb method is providing furnish a good approximation. Okay, so summary. The summary is we are going to study the Wkb approximation because it's a kind of approximation that is extremely useful in a certain number of processes, especially for what regards quantum mechanics. Are you, as students in engineering, interested in quantum mechanics? The answer is yes. Okay, because that's something that with which you are going to face with during your work, possibly. I mean, there's plenty of any kind of device now that are working with quantum mechanics. Let's see how can we solve this problem. Basically, we are going to review the two different possibilities that you have for this equation. Let me start by considering the following case. We'll write epsilon squared y prime prime minus kx squared times y equal to 0. Now, this is an equation which is of this class of equations. Nothing different from this class of equation, right? Because I have some, I wrote this as epsilon squared is just something because it's more, will be useful later for simplifying an epsilon. I can write this as just epsilon, but then I will have some square root of epsilon. I don't like the square root of epsilon, so let me write this as epsilon squared. That's actually the same of this kind of equation. What's also here, what's written here? What I'm doing is saying that the non-constant term is strictly negative. Okay, so what I'm doing is to consider this qx to be a strictly negative function. How can I do this? Well, I can rewrite q of x as minus k squared. Why? Because k squared is surely positive, strictly positive. If I put a minus sign in front, it is strictly negative. Then, so what I want to do is to solve this, to find an approximation to the solution of this equation. If k, well, actually, if k squared were constant, cannot close this one otherwise. Let's try with this configuration. And rewind. So if k squared were constant, then I would be able to write this solution of this equation as a linear combination of exponentials. So basically, the solution, the general solution, would be a linear combination of exponential like e to the plus minus k over epsilon. We want to bet? We can try. Actually, let's try, for example, e to the plus k over epsilon. So the second derivative give me k squared over epsilon squared times e to the k over epsilon, and there is an epsilon squared in front, which is here. Then I have minus k squared times e to the k over epsilon. This simplify with this simplify with this is equal to 0. So the solution e to the plus k divided by epsilon is a solution. You can prove exactly the same that also e to the minus k over epsilon is a solution of this. So the general solution is a linear combination of the two exponentials. This happens in any case. This is true for what? For k constant. But k is not constant. K is a function of x. If it's a function of x, what can I do? An ansatz, and try to see what happens to my ansatz. So let's see what happens if I'm looking for a solution y of x, which is of the form exponential of some function u of x over epsilon. So I'm looking for a solution that looks like this one, but with the function u instead than the constant value k.
Now we are considering k not a constant.
K is not constant, so this is the k equal to constant is just to drive my imagination, because otherwise I can give you some I don't know, stupid answers which is completely out of reality, which can also give you some solution, but in any case it would be very difficult to be so lucky to get the right function. In this case, we are not sure to be able to find a solution with these ansatz, but we know that the ansatz works if u of x is a constant. If u of x is a constant equal to k, if u of x is a constant equal to k, this would give me a good solution. So this is an ansatz, which is a reasonable ansatz. Fine, let's see what happens. Then epsilon squared times y prime prime, so let me write this exponential of u over epsilon prime prime minus k squared of x exponential of u of x over epsilon equal to 0. Now I have epsilon squared. The first derivative of this object gives me I have to do the derivative of this exponential. So this is the derivative of this object of the exponent and the exponential. So this is gonna be 1 over epsilon times u prime times the exponential of u over epsilon prime. Right? I've done only the first derivative. Minus k squared exponential of u over epsilon equal to 0. Guys, notes that sometimes I'm writing explicitly the dependence on x, sometimes I do not write the dependence on x. I hope that this will be clear from the context. So there is, for example, a dependence on x here, a dependence on x here, and so on. Now what I have to do is to do the derivative of this object, which is in parentheses. So I have epsilon squared in front of the parentheses. Now I have the derivative of the first one, which is giving me 1 over epsilon u prime prime times the exponential of u over epsilon plus the derivative of the second term. So it's 1 over epsilon u prime times the derivative of the exponential, which gives me 1 over epsilon, so 1 over epsilon squared, u prime, so u prime squared, times the exponential of u over epsilon, minus k squared exponential of u over epsilon equal to 0. Good. What can I do here? I can simplify the exponential that it is in the three terms. What can I do more? Well, I can write explicitly this product of epsilon squared with the parentheses, and I get epsilon times u prime prime plus u prime squared minus k squared equal to 0. What now? We have solved a couple of problems like this one in the past weeks. Do you remember some technique for solving a problem where you have the u prime prime and u prime squared?
T equal to u prime. Yeah.
Bravo, yeah. Let me write v because t, we were using. So let's say v is equal to u prime, and then I have epsilon v prime plus v squared minus k squared equal to 0. Now let's try the regular perturbation method. So let's look for a solution which is solution Vx equal to V naught of x plus epsilon V1 of x plus epsilon squared V2 of x, etc. If I'm putting these ansatz, so the regular perturbation expansion, in the second equation, what I get is epsilon that multiplies v0 prime plus epsilon v1 prime plus higher order. Then I have plus the this term here, v squared. So v squared gives me v0 squared plus 2 epsilon v0 v1 plus epsilon squared v1 squared plus higher order things. Well, actually there is another terms which is of second order. Which is 2 epsilon squared v0 v2. I'm not going to use this in any case. Minus k squared equal to 0. So now you remember, actually the idea is that I'm taking the the orders which have, sorry, the terms which have the same order in epsilon. So I'm taking, for example, 0 order in epsilon. It's this one and this one. v0 squared minus k squared equal to 0. Then let me take first order in epsilon. This one, and nothing else. So it's v0 prime plus 2 v0 v1 equal to 0. Higher order terms, which I don't care. Now the solution to the first equation is simple. It's v0 equal to plus or minus k of x. The solution to the second one is v1 equal to minus v0 prime over 2 v0. but we know what's V0 because we know that V0 is plus or minus K. So this is minus K prime divided by 2K prime of X, K of X. Then higher order terms that I don't care. So if I'm using the regular perturbation method, the regular perturbation expansion, what I find is a solution Vx equal to V0, we say that it's plus or minus K of X. Then plus epsilon times V1, which is minus K prime over 2K. Plus higher order terms. In any case, what I have to find is u, not v. Remember, u prime is equal to v. So if u prime is equal to v, u is going to be v of v. U is equal to the integral between a and x plus or minus k of c index c minus epsilon over 2 integral of between a and x of k prime of over x over k in the c plus higher order stuff. Note that I brought here this a as the lower limit. This is basically something that should be told to you by the problem, right? By the conditions that you have, initial conditions or the boundary conditions that you have for your problem. Let me leave it as a. So the first term is as it is, it's plus minus the integral between a and x of k of c index c. The second term, what's the integral of the second term? Yeah. So the integral of the second term is some log of k of zeta evaluated between a and x plus higher order terms. In reality, what I want to do is just to consider the term which is minus epsilon halves of log k of x. This would be this term minus the term evaluated in A, which is a constant. Suppose that I'm reabsorbing this constant in, for example, the constant here, or in the terms, the higher terms. It's a constant. I can reabsorb wherever I want. I don't care about the constant part for the moment. So this gives me a solution for u. This is still not the end of the problem, because my state variable is not u. My state variable is y. What I'm trying to find is, remember, the wave function of the particle was factorized in a temporal part, our function phi, times a spatial part, which is our function y of x, right? So y of x was that function that we defined as the exponential of u of x over epsilon. What we've done is to find this u. So we know that this thing is exponential of 1 over epsilon, which multiplies plus or minus the integral between a and x of k c index c minus epsilon over 2 log k of x plus higher order terms. What's interesting here? What I can do here? What I can do the following. I can write this as exponential of 1 over epsilon plus minus 1 over epsilon integral a between a and x of k c the c plus higher order terms times the exponential of 1 over epsilon times minus epsilon halves log k of x. Is this very... Is this a scandal? Okay, why do I want to do this? Well, it's clear why, because epsilon here can simplify. That's not just only this, I can rewrite this term here as the exponential of log of k of x to the power minus 1 over 2. Right. No, rather than doing this, let me write this as minus this to the power 1, 2. Well, it would be the same. Yeah. And what is this thing? This is, well, 1 over the exponential of log of the square root of k of x. But what is the exponential of the log? Is the argument. So this thing is 1 over square root of k of x. Now I'm quite satisfied, because now I can write the solution y of x, this is y of x, equal to 1 over square root of k times the exponential of plus minus 1 over epsilon, the integral between a and x of k of c, the c plus higher order terms. I can forget about the other higher order terms for the moment. Yeah, these this way. So this gives me the two linearly independent solution, approximate solution for the problem. which corresponds to the plus and minus sign of this y. So the linear combination of these two independent solutions give me the Wkb approximation of the solution of the Schrödinger equation. So y of Wkb approximation is going to be the linear combination of these two solutions. So it's going to be C1 divided by the square root of k times the exponential of 1 over epsilon integral a between a and x of k index c. And the second independent solution, which is C2 divided by the square root of k of x times the exponential of minus 1 over epsilon times the same integral.
What is 1 plus O?
This thing here, it's just a way for writing this thing here. Indeed, if you multiply by 1, so the first part is what you obtain multiplying by 1, right? And you would obtain this times this, right? If I multiply this thing here by 1, I get this times this part here. If I multiply this thing here by order epsilon squared, what I get is the higher order terms of this expression. These are higher order again. This is an approximated solution. This is not an exact solution. Since it's an approximated solution, of course, what I'm doing is to forget about terms which are smaller than those that are already in my approximated solution. Okay, and this is one of the possibility for one of the two possible choice of the equation. You remember we were solving the equation epsilon squared y prime prime minus k squared y equal to 0. What happens instead if I want to solve instead of this equation here? So instead of having a non-constant term which is strictly negative, I have a non-constant term which is strictly positive. We are going to solve these two things because these are basically the two usual situations in physics that you find in physics. The procedure is basically the same. It's the very same. What's the difference? And no. What's the difference? The difference is in the constant solution. The constant solution. In the solutions that you can get if you suppose that k is constant. Because now the solution for k equal to constant is not anymore something that goes like this. If you try to put this this solution into your equation, this doesn't work. What instead is a good solution for k equal to constant is this one. You have the I, the extra I appearing here. So basically, in order to find the Wkb approximation for the solution of this equation, what should I do? Should proceed as before, so I can look for a solution y of x with the ansatz, which is exponential of I u of x over epsilon. Guys, do you remember what's this?
Sine theta plus I cosine theta.
Yeah, probably also Mabubi has said the same thing. In any case, it's a cos theta plus I sin theta. So basically, if I'm looking to a solution of this kind, you can already probably understand that the kind of solution that will be my WKB approximation is going to be some in terms of sine and cosine. Indeed, if I'm not going to do the same procedure as before, because believe me, it's exactly the same. Try to do this because it's a good exercise, but it's exactly the same. What you will find is that the WKB approximation of this of the solution of this equation is of this kind: C1 over square root of k times the exponential of I over epsilon integral of this thing plus C2 over square root of k exponential of minus I over epsilon integral of a and x k c d c. And as you can see, this is exactly equal to this one, identical to this one, but with the I here in front, right? This I here and this I here. However, if you use the expression, this expression here, to this identity here to express the exponential of I theta as cosine and sine, what I will get here is some C tilde 1, which depends on C1 and C2, divided by the square root of k, times the sine of 1 over epsilon integral of k plus a C tilde 2, which is which depends on C1 and C2, divided by the square root of k times the cosine of 1 over epsilon integral of a and x between a and x of k of c in the c. Try to do the transformation from here to here. And remember that the cosine of minus x is equal to the cosine of x, and that the sine of minus x is equal to minus sine of x.
The C theta, why depends both from C1 and C2?
Prova. Ah. Actually, if I remember correctly, so basically, I don't remember which one of the two is the one should be C1 plus C2, and the other one should be something like C1 minus C2. Now, what I would like to do today is to use the Wkb approximation for solving another kind of problem, which is the third class of problems that I was showing you before, which is this class of problem. So what I want to solve is what I want to solve. I would like to find an approximate solution to this equation, this differential equation, where lambda is a large parameter. So usually when you have this kind of equation, you can say that lambda is an eigenvalue for the problem if there exists a solution for that value of lambda. So lambda tilde is an eigenvalue for the problem if exists a solution to the problem for lambda tilde. You see, actually, this is not guaranteed. In principle, you can find some lambda that does not give any solution to this problem. That would not be an eigenvalue. Those lambdas for which this problem has a solution are eigenvalues of the problem. So, let me then use the trick to solve this equation, to transform this equation to one of the equations that we have solved before, right? The one with epsilon, the one with the small parameter. So the idea is that I can define some parameter epsilon. This epsilon is equal to 1 over the square root of lambda. Square root of lambda again, because I do not want at a certain point to have some square root of epsilon. Let me define a function k of x to be equal to the square root of q of x. Then what happens to this equation here? This equation here becomes y prime prime plus k squared of x divided by epsilon squared times y equal to 0. Let me multiply by epsilon squared. I have the same equation of before. Equation of before, which I know the approximated solution, which is the Wkb approximation for the solution of this equation, which I can rewrite here. I'm going to rewrite the solution, WKB approximation directly in terms of Q and lambda, okay? So what you have to do is just to take the solution here and then substitute to k the square root of q and to epsilon the square root of lambda. So what you get is 1 over q to the power 1/4 times c1 times sine square root of lambda integral between 0 and x square root of q dc plus c2 times the cosine square root of lambda integral between 0 and x square root of q index c. Ecco qua. Now what should I do is to impose the boundary conditions. In this case, note that I do not have initial value. This is not an initial value problem, it's a boundary value problem. Because I have the value of y on the boundaries of my domain, in this case 0 and pi. So what I can do is to impose that the approximation in 0 is equal to 0, but in 0, this means that I have to take x equal to 0. All right. What happens to this integral? If I'm taking x equal to 0 in these integrals, it's what? What is that? 0. It's 0. So this should be 1 over q to the power 1/4 evaluated in 0 times c1 times the sine of 0 plus c2 times the cosine of 0. No? But the sine of 0, what? It's 0. This term is for sure not here. The cosine of 0 is 1. So this equation tells me that C2 is equal to 0. I'm supposing that Q does not have zeros. If you have zeros in Q, that's a problem. That's a problem. Well, we will have something which is called the turning point. Let's make things simple. So consider the fact that Q does not have zeros in 0. Well, does not have zeros in, if you want, in 0 pi greco, in the interval 0 pi greco. Okay, so this first condition tells me that CQ must be equal to 0. What's the second condition? The second condition tells me that Wkb in phi is equal to 0. What is this quantity? This is now it's C1 divided by Q to the power 1/4 evaluated in pi. Times the sine of square root of lambda times the integral between 0 and pi of square root of q of c, the c. This thing here must be equal to 0. But what are the possible choices that I can do to make this expression equal to 0? There are at least two possibilities that I have. What's the first one? The simple one.
C1 equal to 0.
Very good. Who is it? Ah, Nicolo. Yes. The first possibility is
Yeah.
C1 equal to 0. Oh, Andrea. Well, Andrea, I don't know, somebody of you two guys. C1 is equal to 0 is one of the two possibilities. What happens if C1 is equal to 0? Guys, the answer is very simple. Come on. What happens if C1 is equal to 0?
Everything is equal to 0.
The entire solution is equal to 0. So this is the trivial solution. We don't care about the trivial solution. Okay, that's fine. There is a trivial solution which is equal to 0. Fantastic. That's the solution that we don't care. We want the other solution. So forget about C1 equal to 0. Suppose that C1 is different from 0. What's the other possibility? The other possibility is that this quantity here is equal to 0. So it's sine of square root of lambda integral between 0 and pi of the square root of q equal to 0.
Why there is close the cosine? Cosine.
Why? Tell me.
Why?
Why? Why?
Because it's symmetric. So
No, it's because imposing the first condition C2 is equal to 0. So we impose the first condition and we forget about C2. We are looking for a non-trivial solution, but C2 equal to 0 can give me some non-trivial solution, which is actually the one that we are finding now. That's why you don't have the cosine part. Then, what are the what this condition tells me? This condition tells me that when is this condition satisfied? This condition is satisfied when the square root of lambda times the integral between 0 and pi of the square root of q, the c, is equal to così. Sì, no. Se questo è 0, quando è che questo è 0? Quando è che questo segno è 0? Solo quando è 0. Just when this is 0. Very good. So this is, well, you can write it this way. So this quantity here, when this quantity here is a multiple of pi, this sign is equal to 0. This sign is equal to 0. Not something which is right. This is something which is important. Remember that this approximation, this is an approximation for the case in which lambda is large. So this was our problem. Our problem is lambda is large. What happens then on n? N. N are numbers. Which numbers? Can it be 1 or 2, 3, 4, 5? These must be large numbers. not infinity necessarily, but large numbers, because I'm looking for a solution for lambda which is big. So basically this means that this approximation is valid for large n. Finally, let's find the lambdas. So the eigenvalues, the lambdas for which this problem has a solution. So these are lambda n that I can write in terms of this n pi. It's going to be n squared pi squared times the integral of the square root of qc, index c, everything to minus 2. Okay, this is becoming a bit complicated. Right? So these are the numbers, lambdas, for which your problem have a solution. So these are the eigenvalues of the problem. And you can find also the corresponding eigenfunction, well, the Wkb approximation of the eigenfunctions, which are then those equivalent to lambda, these lambda n's. So Wkb, the Ywkb is written here. What I have to do is just to substitute the lambda, I have to substitute the lambda n. So this is gonna be, it's written here in the notes, C1 divided by qx to the power 1/4 times the sine of n pi, which multiplies the integral between 0 and x of square root of q, divided by the integral between 0 and pi of the square root of q. Questions so far?
I have a question. So the WKB approximation consists only to find an initial possible solution, an initial form solution.
Usually that's always of this kind, of exponential blah blah blah.
But after we use the regular perturbation method.
You use in the middle also the regular perturbation method. Yeah. So basically, it's a way to implement the regular perturbation method for those equations which you can write as epsilon times the highest derivative of the ordinary differential equation plus other stuff. Then you do these ansatz in terms of either exponential or sine and cosine, do the regular perturbation method, and blah blah blah. Actually, indeed, you can also call them, it's kind of application, it's not even a method itself, because it's an application of methods that we have already studied. But has its importance, again, because it's basically the way physicists do calculations for quantum systems, basically. For these kind of systems, you don't find, well, there are few exact solutions. Usually, you are looking for approximate solutions. There are some exact solutions of quantum mechanical systems, but of wave functions of quantum mechanical systems, but usually you find you look for approximate solutions. Okay, since it's 35, what I can do in 10 minutes? In the next 10 minutes, what we can do is instead to introduce something that we are going to finish tomorrow. I'm not going to arrive to 4 p.m. For this lecture. I'm finishing 10 minutes before, but I cannot finish now. So we can introduce this problem. All right. The problem is that usually sometimes the kind of solution that you can find to your initial value problem or your boundary value problem is not written in a closed form. So you do not have a function that you can easily recognize as something that you already have already seen. Let me give you an example. Are you able to do this? Are you able to do this? Oh, let me open a new section. This integral. Yeah. This looks a simple integral. This is not a simple integral. So this integral is the integral that you get, is the solution that you get if you try to solve the following problem. With initial values given by y of 0 equal to 0 and y prime in 0 equal to 1. So if you try to solve this problem, the solution that you get is this object here. And you can easily see this. How can you see this? In this way, consider the derivative of y. This would y prime. What's y prime? It's this thing, correct? If y is the integral of this, y prime is this thing. What's y prime prime then? Is the derivative of this thing, which is minus 2 lambda t times the exponential. No? Then if I do y prime prime plus 2 lambda t y prime, this is minus 2 lambda t e minus lambda t squared plus 2 lambda t e to the minus lambda t squared, and this is equal to 0. All right, this is a solution. Can you find this integral? Can you calculate this integral? I am not answer. I can already tell you. I don't believe that you can do that. Well, possibly it's also possible that somebody of you has already studied this kind of integrals. So if you did, just tell me. This can be written in terms of a function which is called the error function, whose definition is the integral between 0 and t of the exponential of minus lambda s squared. Okay? So the point is that sometimes you are not able to find some kind of a solution with a nice form for your problem. But sometimes you don't care, you don't even care of these things. Sometimes what you really just care is the behavior of your solution in some in some conditions. For example, what happens asymptotically for the solution. So let's see how is it possible to deduce some other informations about the solution of this problem that solution that can be written in this way. In particular, we are interested to try to find information from the integrals that can be written as this thing here, e to the minus lambda g of t in the t. So g is supposed to be an increasing function, strictly increasing function in a b, like t squared or like t. And we can try to use some information for lambda, which is very large. Basically, this is equivalent to say that we are looking information for lambda that goes to infinity. Now it was the case of saying infinity. So, for example, what happens for the integral that I will define some quantity j as the integral between 0 and infinity of sine t over t times the exponential of minus lambda t in the t, where lambda is very large. That's exactly the kind perché entrano sempre vespe qua? That's exactly the kind of integral that would enter in this the kind of integrals that would enter in this class. Well, what we can do is to split this integral into parts. That's something that I can surely do. Right? What's special in the second one, the second term? Well, we can try to put a limit to some kind of constraint on this term. What we can do is to consider the absolute value of the integral of this integral. We know that this is smaller or equal to the integral of the absolute value of sin t divided by t times e minus lambda t. So this should be the absolute value of the entire integral. But of course, e to the minus lambda t, it's always positive. So this is equal to the absolute value of sin t over t times e to the minus lambda t in the t. What's the maximum of sin t over t? The maximum is 1. So surely this thing is less than the integral between t and infinity of 1 times the exponential of minus lambda t. You can calculate this integral. That's the exponential of e minus lambda capital T divided by lambda. What happens to this term when lambda is large? This goes to 0. For lambda goes to infinity, this term goes to 0. So the second term, this one, for very large lambda, goes to 0. Let's see what happens instead to the first term. So the first term is the integral of between 0 and t of sine of t over t times e to the minus lambda t in the t. Now I can suppose that t, capital T, so this capital T here, is small enough. And then what I can do is to look for the Taylor expansion of sine of t over t close to 0. And this would be 1 minus t squared over 3 factorial plus other term in the t. Am I allowed to do that? Yes, I can choose a very, very small t, capital T, in such a way that in this interval, this expression holds. The other part goes to 0 for very large lambda, so I can forget about that. So I will have just this expression. There is also the exponential here. There is also the exponential, sorry.
Sorry, t squared or 2?
T squared over 6, yeah. This is sine t over t. Sine t is t minus t cube over 3 factorial plus t to the 5 over 5 factorial, so forth and so on. If you divide by t, you get this. Yeah, it's this expression here. This one, you can calculate this thing. Well, what you can do is to do the transformation lambda t equal to u, and this expression gives you 1 over lambda times the integral. Yeah, this is the integral of lambda t. Of 1 minus u squared over 6 lambda squared plus higher order terms e minus u, the u. Notice that this one is now lambda t. Now, t, capital T, is, we say that it is, we can choose it small, but it's fixed. Once that I choose t to be small, but fixed, I can always choose lambda to be extremely large, because that's actually what I want to do. I want to study what happens in the asymptotic limit for lambda, when lambda goes to infinity. Basically, this means that I can take the integral here from 0 to infinity of this thing here. Good. what now you have to use is this integral. If you don't know this integral, try to calculate it. You should be able to calculate it, integrating by parts. This is something which should be easy to do. This is m factorial, the exclamation mark is for factorial, m factorial. Then if you use this thing, you can finally express the integral j. You can perform this integral and finding the quantity j that was this that we were interested in for large lambda as 1 over lambda minus 2 factorial over 3 factorial lambda cube plus higher order terms. This is interesting because this way you are not obliged to calculate explicitly this integral that you don't know how to calculate, but you can in any case know how does the integral behave for very large lambda. So for very large lambda, this integral behaves as 1 over lambda plus corrections. And I would close here. For today, questions. If you don't have the questions, you can go home. Nothing. All right, guys. Talk to you tomorrow then. Cheers to everybody. Grazie a voi.
Giornata.
Thank you, Professor.
Cheers.
Arrivederci, prof. Saluti.
Ciao.
Bye, Professor.
Buona serata.